The electric force between 2 point charges is, we call this the Coulomb force, and we read it something like this. The magnitude of the electric force equals 1 over 4 pi epsilon naught, a constant of nature, times Q1, Q2 over r squared. Like gravitational force, electric force falls off rapidly as you increase the distance between the centers of the two charged objects. It's also an inverse square law, so we can say that the electric force is again proportional to 1 over r squared. Consider Q1 to be a tiny test charge. The force to test charge ratio is the electric field strength. This gives us a new equation for electric field strength. Electric field is also inversely proportional to the center-to-center distance between the two objects. The derivation of the electric potential for a point charge requires calculus, but the equation is this. To calculate the electric potential difference between any 2 points in an electric field, we could use this relation. The change in potential, the change in electric potential, equals 1 over 4 pi epsilon naught times Q times 1 over final position minus 1 over initial position. To calculate the change in electric potential energy when moving an object with charge in an electric field, we can use this relation. Delta U equals Q delta V. Change in electric potential energy equals the product of charge and potential difference. Although electric field is a vector, electric potential is a scalar. If you divide electric potential energy by electric charge, two scalars, you end up with a scalar. Let's look at the equipotential lines around a fixed positive point charge. Just like the gravitational potentials around a spherical mass like Earth, these will be concentric circles. And again, just like Earth, the differences in potential will not be accompanied by an equal difference in distance. This representation of electric potential around a positive point charge is analogous to the representation of gravitational potential around Earth. Our loose definition of electric potential is electric potential energy for every unit of charge. Let's add electric field vectors to the diagram. They point radially outwards because the force on a positive test charge is repulsive, and they get shorter farther away from the source of the field because the field has an inverse square relationship. The average value of the electric field in a region equals the change in electric potential across that region divided by the change in position in the relevant direction. Or the absolute value of E equals the absolute value of delta V divided by delta R. That means that we could calculate a value for the average electric field strength for any 2 points if we know the potential difference between those 2 points. We would divide the potential difference by the distance between the 2 points. In electrostatics, we use tiny positive test charges to imagine what happens in regions with electric fields. Imagine moving a tiny positive test charge from an initial position near the edge of the diagram to another position closer to the center of the diagram. You would be pushing the tiny positive test charge closer to the positive charge at the center. The electric field points in the opposite direction, so you're working on the system. It's like pushing the object uphill. You're moving the test charge from low potential to a higher potential. If you released the test charge, it would gain kinetic energy. It would speed up as it moves from higher potential to lower potential. Now it's time for you to practice with some of these concepts by doing an activity.